All right, let's find the 6th degree Maclaurin polynomial for cosine x. So think back to your parent series for cosine. Okay, we should be able to create all the way up to the 6th degree term. All right, so if you see these instructions to find the 6th degree Maclaurin polynomial, it's through this method of finding the functional value at the center, which is 0, and finding up to 6 derivatives, evaluating it at the center, and then thinking about the structure of our Taylor polynomials. Okay, I think I'm going to take a different approach. You decide what you like as far as comparing and contrasting this with example 1. I'm going to calculate all 6 derivatives, and then I'm going to come over here and calculate the values of those, as opposed to like what I did on example 1, just to provide a different, approach. You can choose whatever you care for. And with the 4th derivative, we're back to where we started with the original function. Okay, and so over here in this column I'm going to find the functional values and the derivative values. I'll find the functional value at 0 at the center and all the derivatives at the center. All right, so f of 0, cosine of 0 is 1. Okay, so it appears that, let's see, the derivatives, at least the odd derivatives, are going to have a 0 value. The even derivatives are going to either be positive or negative 1. This was the 3rd derivative, and that was actually 2. So we're alternating positive 1, negative 1, etc. through the even powers. Even derivatives, not powers, derivatives. All right, I think we have everything we need to do to build the 6th degree polynomial. So polynomial of 6th degree. Looking back at the formula, so to speak, it's the functional value at the center. So we're going to start with 1. Okay, then we're going to add f prime at 0 divided by 1 factorial. Well, f prime is 0, 0, so we're not going to have that odd term there. So I'm going to go over to the 2nd degree term. Because the center is 0, I'm just going to go straight to x squared. The 2nd derivative evaluated at 0. I'll come back and build this in a minute. Over 2 factorial. I'm not going to have a 3rd degree term, nor am I going to have a 5th degree term, but I will have a 4th and a 6th. Okay, and for the 4th degree term, degree 4, 4 factorial, 4th derivative will be placed in here. Okay, the 2nd derivative at 0 is actually minus 1, so we're going to have minus x squared over 2 factorial. The 4th derivative at 0 is 1, so I'll just stack this. X to the 4th over 4 factorial. 6th degree at 0, or 6th derivative at 0 is negative 1. So minus x to the 6th over 6 factorial. Okay. So there we have it. Okay, so let's just kind of pay attention to, when we're reading a problem, make sure you understand, are they asking me to find a series or are they asking me to find a polynomial? Because that determines, the amount of work you're going to put into it. All right, find a Maclaurin series. So I would start this way with this. I would generate enough terms, I don't know, 3, 4, 5 terms, do exactly this right here, and then just indicate with a plus dot 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 that it's a series, not a polynomial. But you might want to be aware, are they asking me to find the nth term expression? Oftentimes they are. All right, so how does it look as far as, how does it look a little differently? Well, this, notation is reserved for polynomial. This is f of x equals, we're working with what, cosine? And that's going to be equal to, I'll just steal what I did previous. So I've gone through all this. I know it continues, so I suggest that it does. I'm probably going to be asked to find an expression for the nth term. Okay, and like mentioned earlier, you might want to call this term the 0 term, or it's in position 0, 1, 2, 3. So looking for a pattern from the term number, the position, okay, and the degree, and then from there it's kind of easy to build. Okay, it is alternating in sign. Okay, so I'm going to start with -1. If I raise it to the n power and n starts with 0, that's okay. It's going to start off positive. If I raise -1 to the first power, it's going to become negative, and then from there on, etc., I'll have the correct sign. Okay, what do I do to 1 to get 2? What do I do to position 2 to get the number 4, 3 to 6? I'm doubling. So I have a base of x, and I'm doubling the n value. Okay, and I'm going to divide that by 2n factorial. Okay, and you could actually, write this in summation notation, collapse it. Okay. Just again, read the problem, make sure and pay attention to what's being requested. I'm sure either will be acceptable, but if they're explicit about what they want, they would say that. All right, example 3. Find the 5th degree Maclaurin polynomial for e to the x. Again, that's one of the parent series, power series that we started with when we started our look at series. So we do know what the first 5 terms look like, okay, hopefully. All right, and so we're going to actually go about creating those first 5 terms, or 5th degree, I should say. All right, find the 5th degree Maclaurin polynomial. Okay, so we need the functional value at c equals 0, that's our center, and then we need 5 derivatives of e to the x evaluated at the center. It should be pretty easy. All right, so what's a polynomial that when graphed in the same window as this exponential function, it models it closely around the center? Well, we're about to find out. Pretend we don't know. Oh, easy. Love the exponential function, the natural exponential function, for this very reason. So we're going to evaluate the function and all the derivatives at c equals 0. So f of 0, e to the 0, nice, is 1. Very nice. I'm just going to skip that middle step there and say, yeah, it's 1. Okay, you can either go down below here, or I tried to save you a lot of room here. All right, so the functional value at the center. Okay, the second term is the first derivative evaluated at the center divided by 1 factorial times x minus the center, or just x in this case. It's the linear piece. Okay, next term, second derivative evaluated at the center over 2 factorial, etc., x squared. So I'm just kind of putting the formula here. I think I'm losing my little primes. Okay, and I can hear some of you guys just thinking, am I going to have to, do this structure the whole time if I know what the answer is? No. If you need to go straight to this 5th degree polynomial, then that's fine. The first derivative is going to be 1 over 1, or just x. The second derivative is also going to be 1, so just stack this as x squared over 2 factorial. I'm going to be patient, hoping it comes back. Okay, the third derivative evaluated at 0 is 1, so plus x cubed over 3 factorial. So we can see the 5th degree polynomial. If you had been asked to find a Maclaurin series, then you would know to go plus ... and look for an expression for the nth term. I kept thinking it would reappear, but apparently not. So I'm going to do one more example and hope that all goes well. So you better write quick so you don't lose it. Okay, so you might recognize this function from one of the 4-parent series that we're expected to know and recall quickly and easily. So, and I just gave it to you in the beginning of the unit. So now, where did all those terms come from? Well, from the formula that we just saw earlier on the other side of this page. So find a Maclaurin series. The center is 0. So we're going to evaluate the function and all its derivatives at 0 and go from there to create the series that we already know should be. I'm going to pull up the denominator. Oh. Finding the derivative using the chain rule. Times the derivative of the, that's a minus right now, times the derivative of the inside function, which is going to be -1. So if I did clean this up, oh my goodness, it's going to be 1 minus x, that's an equals, to the negative 2. I'll change colors. I wonder if that's it, or at least make it thicker. I'll try. Okay, so that's still the first derivative. Let me find the second derivative. Drop the exponent to negative 3, multiply by the derivative of the inside, which will be negative, so that's going to make that positive. Oh, I think that was the second derivative. Okay, so the third derivative is going to be negative. Oh, I don't even know what that is. All right, trying an entirely different color, the third derivative. Negative 6 quantity 1 minus x to the negative 4 times the derivative of the inside, which will cause that to be positive. So I'm seeing a pattern here. So how many of these do we have to do? Well, enough to kind of get an idea of what's going on here. Okay, I believe that was 1 minus x to the negative 4. So this is frustrating for you as it is for me, I'm sure. So why don't you generate maybe 1 or 2 more derivatives, pause the video and do that, and I'll get them on here too. Okay, now the scary task of making sure and evaluating the the function of the derivatives at the center 0. So it probably would have been helpful to kind of stack it as a fraction. This is 1 over 1 minus x squared, so that looks like f prime of 0 is also going to be 1. All right, f double prime of 0. Well, the 2 would be in the numerator. This would be in the denominator. X is 0, so that's just a 1, so it looks like I'm going to have 2. All right, the third derivative appears to be 6, or as evaluated at 0 is 6. The fourth derivative at 0 is going to be the coefficient 24, and maybe one more. How many do you know how to do? Well, just until you feel like you have enough to develop a pattern. This is 120. All right, a power series representation would be 1 plus, okay, for the Taylor formula, it's the first derivative divided by 1 factorial times x minus the center, so it's just going to be x, plus, and the next term is going to be the second derivative, 2 divided by 2 factorial. So 2 divided by 2 factorial is going to cancel to 1, plus, all right, the next coefficient would be the third derivative, which is 6 divided by 3 factorial times x cubed. Next term, 4 factorial down here, x to the 4th here, but the coefficient that has magically disappeared was 24. And I think I'll just do one more. Plus, well, that's all I have. Plus 120 over 5 factorial times x to the 5th plus dot, dot, dot. So if we're asked to come up with an expression for the nth term, that's where we would want to maybe indicate the position number as far as 0, 1, 2, 3, 4, 5, etc., and come up with that. Okay, I'm going to do a little cleanup here. 6 is actually 3 factorial, so that'll clean up nicely to x cubed. 24 is actually 4 factorial, so that'll divide out, and we'll have x to the 4th plus dot, 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 plus it's going to be x to the n plus dot, dot, dot. So if we wanted to, we could collapse this into sigma notation as well, and it's actually indeed what we got previous, or what we were given, I guess, previous. Okay, and that's all the time we have. We'll just continue this in class, the rest of this worksheet.